So, chemists like enthalpy a lot. We do so much at constant pressure. Enthalpy is a really important piece of information about reactions, about chemicals. So, we are also going to talk about standard enthalpies of formation and finding a standard enthalpy for a reaction. So, all of this hinged around delta H being a state function. So we can call any point our 0 point. And we've chosen a reasonable reference called the standard state that gets used in the same way across different variables. So we've chosen a reasonable 0 point. This will also give us another way to get delta H reaction. So our 0 point is the standard state. The standard state of a substance means that if you have a pure gas, the pressure of that gas is 1 atmosphere and the temperature is 25 degrees. If you have a liquid or a solid, it's pure, it's in its most stable form, it's at 1 atmosphere and 25 degrees. If you have a solution, then the concentration is exactly 1 molar. So if you meet these conditions, then you can say that it is a standard state of that substance. We use this to define standard enthalpy change, which is delta H, but with this little circle, like the little degree symbol in the upper right. The standard enthalpy change is the change in enthalpy for a reaction when all of the products and reactants are in their standard states. So if the components of a reaction are in their standard states, the enthalpy change for that reaction, you can put the little circle on there and say it's a standard enthalpy change. The standard enthalpy of formation, delta H, little circle thing, and an F. This is if you have a pure compound and you have a reaction written where that pure compound is the product and the reactants are the elements in that product but in their standard states, then the enthalpy of formation for that reaction is only the enthalpy of the compound. Because when you have a pure element in its standard state, the enthalpy of formation is 0. Right? If I go pick up oxygen gas, I mean you can't pick up oxygen gas, but if I think about oxygen gas, that's just how it exists. That is the standard state of oxygen gas, of oxygen is as O2 gas. The enthalpy of formation is 0. The enthalpies of formation listed in the appendix, well, first of all, you will see 0 listed for things like oxygen gas. So in case you forget that that is what the enthalpy of formation means, then you'll be able to see that in the table. But for all of the other compounds, it's coming from the reaction that has not been written for you. So, I mean, let's look at an example. If we do solid glucose, so C6H12O6, look at the table for the enthalpy of formation. That value in the table, this negative 1,273.3 kilojoules per mole, comes from the reaction that is listed as the definition of enthalpy of formation. So C6H12O6, carbon, hydrogen, oxygen. If I take carbon in its standard state, so carbon, a solid, graphite is the most stable form, right? The enthalpy of formation for solid graphite carbon is 0. Hydrogen, Standard state is H2 gas. Enthalpy of formation for that is 0. Oxygen, O2 gas is the standard state. So if I take 6 carbon in its standard state, 6 H2, standard state, 3 O2, standard state, use it to form C6H12O6, the delta H reaction for this reaction is negative 1,273.3 kilojoules per mole. Because all of the reactants have an enthalpy of formation of 0, right, all of that energy that's given off is associated with the solid glucose. The way that we use this is that when we have a full reaction that's not necessarily just the formation of that compound, we will be able to put enthalpy of formation values into our products minus reactants equation, because it's secretly like doing Hess's law a bunch of times, except we're making it faster by leaving off the formation of those compounds. So we're just going to know that all of the reactants were zeros, look at the compound that I have and the enthalpy of formation, and then use that in a calculation for a different reaction. So what does the equation look like? It's this one, delta H reaction with a little circle, meaning the standard. It's the sum of the number of moles of product times the enthalpy of formation of those products minus the sum of the number of moles of reactants times the enthalpy of formation of the reactants. So the enthalpy of formations are all listed in kilojoules per mole, and it depends, right? It depends on the number that you use, right? When we multiplied a reaction by 2, we multiplied the enthalpy of that reaction by 2. If I have twice as much, then the enthalpy of formation, I need to use twice as much. So let's try this out for an example. We're going to find the enthalpy of reaction for 4NH3 plus 5O2, turning into 4NO and 6H2O. The enthalpy of reaction I'm looking for, it says delta H reaction with that little 0 circle. That means standard state. That is my clue to use enthalpy of formation. So I'm going to make a little table here and pull in the numbers. Enthalpy of formations, if I go look at, it's in the appendix of the textbook or in the extra long equation sheet that we have for this semester of Gen Chem. The enthalpy of formation for NH3 gas, don't forget to look at the state of the compound that you're looking up, is negative 45.9 in kilojoules per mole. For O2, it's 0. It's the standard state, so that's not surprising. For NO, it's 91.3, and for H2O, it's negative 241.8. Make sure you have the value for H2O gas. So my delta H reaction, just shove a little circle on it, the sum of the number of moles of products times the enthalpy of formation of the product. That means my first product is NO, and there are 4 of them. So 4 moles times the 91.3 kilojoules per mole that I found for NO, plus my next product is water, 6 moles of water times negative 241.8 kilojoules per mole. And then I'm going to subtract the same thing for the reactants. So in the reactants, I have 4 moles of NH3, which is negative 45.9 kilojoules per mole. And then for oxygen, it's a 0. I mean, it's 5 times 0, but that still gives you a 0. I've got brackets here. I will usually find the result of each piece. It's also much easier for me to check your work if you find the result from each piece. In the end, from this, though, you should get negative 902.0 kilojoules. So this reaction overall, it has a negative delta H reaction, is exothermic.